Okay, folks, I wanted to walk through a handful of things on this PowerPoint, kind of like I would in class, but since we're doing this flip thing, I wanted to at least talk through a few things. So first off, one of the fundamental principles of engineering design is we have capacity and demand. So demand being loads or stress, deformation, strain, whatever demands are put onto our structure. And then capacity, we might measure that in strength and stress, deflection, or allowable strain. And there's always variability in both the demand and the capacity. So if we look at a probability curve, there's a place where those intersect and failure will occur. And in the US and most developed countries, that failure rate is about 1 in 10,000. Okay, another thing that's going to be important this semester are strength reduction factors. 0.9 will be common for beams where they're tension controlled, and we'll get into what that means later. Columns will range from 0.65 to 0.75, and then shears 0.75. We'll also get into bearing calcs and some anchorage calcs, and you can see for anchorage, sometimes they're pretty dang low. Okay, so kind of expanding on the strength reduction factors, we have this thing in concrete design called compression controlled or tension controlled, where tension controlled is the rebar is yielding long before the concrete crushes, which is an ideal failure mechanism. Compression controlled is where the concrete crushes, and we want to be a little more careful with that, so we'll apply a strength reduction factor that's smaller than that of a tension controlled member. And this is kind of the crux of this presentation and something that probably the main reason I wanted to make this video for you. All right, so this stuff, I'm just going to let you kind of cruise through this. There's a rebar table here, bars, which tells you the area of steel or the tension capacity. So I've kind of saved you the math of multiplying the area by 60 kibs per inches squared. Cover, so how much clear distance between the edge of the bar and the edge of the concrete. It relates to durability and what the concrete's exposed to. Development length is critical. Basically, how far do you have to put the bar into the concrete for it to develop its full strength? I'll let you read this. There's equations for it. I also have an example of how to calculate it from my book, so you can use this if you want to do it in metric. You can. Anyway, it's pretty simple, and once you run those equations, you can develop tables like this. So depending on the compressive strength, you'll have different development lengths. So I'll let you guys study that and then ask questions. Similarly, for tension, bars in tension that are hooked, development lengths are shorter, and then compression development lengths as well. Lap splices, you can get into that. Okay, so getting into some of the key things. First, when we do concrete design, we need the elastic modulus for certain calcs, and that's a function of the density times the square root of the compressive strength, or you can use 57,000 square root of F prime C for normal weight concrete. It's important whenever you take the square root of the compressive strength of concrete or the square root of anything that you use the right units. I always like to use kibs per square inch, but in this case, when I'm taking the square root, I have to use pounds per square inch, otherwise things get messed up. Okay, there's some discussion on concrete behavior. I'll let you get into this. But the crux of what I want to talk about is this tension controlled type of business. So for compression controlled, like I said earlier, Compression controlled happens when the concrete crushes before the rebar yields. And the problem with that in beams is it doesn't give much warning for failure. So we like to proportion our beams to be tension controlled. So there's at least 200% elongation in the bar before the concrete starts to crush. So if we look at these distributions, if this is our cross section of a beam, we have a compression zone, which is hatched up here. It has some bar in it. And then we have our tension reinforcing. For a compression controlled, if we look at the strain distribution, so we're taking it from the tension, the bottom layer of tension reinforcing to the top of the beam, and we draw a straight line. If we say the strain in the concrete, the crushing strain is 0.003, the yield strain of the bar is 0.0207, and the math for this is on this page, one of these pages here. Yeah, so this data kind of inputs to this conversation. Basically, in this case, the bar yields at the same time it crushes, and that's not what we want. So if we look at a case where the strain in the concrete is 0.003, but the strain in the rebar is already 2.005, which is about twice past yield, then we can say the bar is yielding quite a bit before the concrete is going to crush. And that's the condition that we're kind of aiming for. So if you do the math, you can use similar triangles to develop these equations here. But the bottom line at the end of the day, we want to find a compression control limit over dt, and that's going to be 0.592 times beta 1. And beta 1 changes as a function of compressive strength. And then we do a similar thing for tension control limit, and if you do the math, the similar triangles, and you can play around with that, we get 0.375 beta 1. So then that brings us to this table here. So if we come here for a yield strength of 60 KSI, tension control limit over dt, for 4,000 PSI mud, we have 0.319. And you say, well, that's cool, but what does that really mean for me? So let's just keep this number in mind. And then we're going to calculate, and I don't know if we've done that yet or when we'll do it. We'll do it for sure when we do bending design, so kind of hold tight on this. But the distance A is from the top of the beam or the top of the compressive phase to where it ends. So it's essentially the area of the concrete that balances the strength of the steel. Anyway, so we can calculate A, the depth A here, based on how much bar we have. And then if we divide it by D sub T, which is from the what we call the extreme compression fiber to the outermost layer of bar, so the center of that bar. So if we take A over dt, if it's less than this number, then we're tension controlled. If it's more than that number, then we need to decide, well, is it compression controlled or not? If it's compression controlled, then we need to either make the section bigger or take out bar. So anyway, we're going to use this, excuse me, all semester long to understand the behavior of the concrete. So just to kind of reiterate, you'll calculate A divided by dt, and then depending on your strength, you'll have different values that A over dt needs to be below in order to be tension controlled. And then if it's not, so here's our tension controlled phi factor of 0.9. If it's not, we might be somewhere on this transition curve or fully compression curve control, just depending on that A over dt value. So just to reiterate one more time, we're going to calculate the left side of this, and then this right side we're going to pull from this table or if you want to calc it based on this, you can do that. All right, I think that wraps up what I want to cover for this. So I've given you, like I said, a development length example, pretty basic stuff, but this kind of is the crux of the concrete design, is understanding all of these inputs, and we'll be using them all semester long. So don't worry about having a total mastery at this point. We'll get there as the semester progresses. All right, I'll talk to you guys in class.